Good morning, calculates. So we've been looking at logarithms, natural logs specifically, and today we're going to look at their cousins, the exponential functions. So here I have good old exponential function, e to the x, exponential function because x is in the exponent, and I'd like to find the inverse of it. So if some of you remember, of course, when x is in the exponent, the way to get it out is to log both sides. Now, I'm going to be a little picky on this. If you remember during your PERT problems, that was definitely the application that you used. And when you were solving for either t or r, you chose to use natural log to get it out because the exponential base, right there, is base e. So if I find the inverse, of course, I would have x equals e to the y. And then to get y by itself, I'll natural log both sides, which makes that exponent come down. So I have natural log of x equals y times natural log of e. But of course, natural log of e is 1. So y equals the natural log of x is the inverse of the exponential e to the x. And so here we go. Y is equal to e to x if and only if x is equal to the natural log of y. And of course, when I graph the two inverses, they are mirror reflections about the line y equals x. And of course, some important notes is that on y equals e to the x, I have an asymptote at y equals 0. And on natural log of x, I have an asymptote at x equals 0. And of course, there are mirror reflection points, 0, 1, and 1, 0. And then some properties that you would probably note if you looked right over there to the left at your graph is that the domain for e to the x is negative infinity to positive infinity, but the range is from 0 to infinity. It is continuous, it is increasing, it is 1 to 1. It's concave up everywhere, and as I go to negative infinity, I'm getting closer and closer to that asymptote, aka 0, and as I go to positive infinity, it's just increasing without bound. And you should be able to see all of that in your graph of e to the x. So moving on to the derivative of e to the some power, it's the derivative of the exponent times e to that power. So in other words, if I was doing derivative with respect to x of e to the x, I would get the derivative of the exponent, so that would be 1 times e to the x. So the derivative of e to the x is e to the x. That's pretty crazy, huh? So if I look at this first one and I want the derivative, it's the derivative of the power, so that would be 5 times e to the power. That's pretty simple. Let's look at number 2. Now I got a division, so I've got to use low d high minus high d low all over low squared. So low d high would be 0 minus high d low. Well, the derivative of e to the x is e to the x. And the derivative of this is the derivative of the exponent, so that'll be a negative 1, and then e to the negative x all over low squared. And I could probably tidy that up to become just that. On to the next video, kids!